Hello, hello everyone. How is it going? How is it going? Hope it's a good Saturday. Hope it's a good Saturday. I couldn't come live yesterday because I was very sick. I couldn't even get up from the bed for the entire day. Yeah, it was pretty bad yesterday. Yeah, today I'm feeling better since morning. I have recovered a lot. There is still a little bit weakness, so I might talk a little less. Sorry for that. But yeah, I thought, okay, what good can it be? Uh, like the entire day's work is already done, and I was thinking what to do right now. I was like, okay, we don't have plans to go out or anything, so I'll go ahead and stream a little bit, and I'm gonna start a new topic today. And as you can see in the title, I've been meaning to start this for a very long time, but I couldn't. I couldn't, and this basically is like it's gonna be the journey which says that okay, this is from the ground up learning how machine learning works. Believe it or not, 2016 was the first time. I don't know how many people, like I'm pretty sure many people were already knowing about like what the trend is gonna be, what the future is gonna be. They were already working towards it because AI, machine learning research and work is not just new. All of a sudden, it come in. There was GPT-1, then GPT-2, then GPT-3, which is when people actually came to know about And once I started using it, I was like, okay, it's pretty damn bad. What the fuck is going on? 3.5 was still bad, but then when 4 came out, I was like, okay, now it's really helpful and it can do some stuff. But yeah. So this research has been going on since 1970s or something like that, right? It's not just now, but now the technology is at a certain point where it can be monetized, where companies can actually monetize out of this technology, and that is why it's coming more into limelight. That's what it is, right? That's how it has been. That's what it is, I feel. But yeah, coming to the main point. So 2016, I got my first MacBook Air, and I started off 2016, late 2016, and early 2017, I actually did for the first time a complete course of Python. I don't know how many people were doing Python back then, but a lot of my friends were still doing Java, Spring Boot, Spring. I don't think Spring Boot was a thing back then. In 2017 at least, 2019 I think Spring Boot. Spring Boot history. No, 2014 it first came out, 2018. So yeah, so 2018 is when I first heard about this thing called Spring Boot. 2018 or 2019, I don't quite remember. 2019 I think, not even 18. But before that I actually did Python, and like at that time again, my entire thought process was languages. It was never like concepts, but yeah, I got pretty good with Python, writing scripts and things like that. Writing applications of how, like pretty advanced topics of Python I actually went through. But then I never really what is it called? Like never really got into machine learning. The entire idea was that okay, once I learned Python, and I also learned a little bit of R. By the way, I completely forgot, but I learned a little bit of R for a month or so. But the entire point was that like it should now start working towards more machine learning stuff. But then since I absolutely loved maths during my school days, but then slowly over time that love just faded away from maths. So I was always like, okay, I don't want to touch it. I don't want to touch it. I don't want to touch it. But now I wouldn't say for the love of it, but for the point that you should learn machine learning. And I don't want to be the person or the engineer who just keeps using AI tools. I want to be the person who understands how an AI tool works behind the scene, and how a model works behind the scene, and how better I can work with different algorithms. Okay, so that being the goal, I think one of the more important things is that I have to understand from the first principles. I understand the maths behind it, understand like the basic structures and the maths which powers these algorithms, right? That's one thing. And another, and another thing is, let me share my screen. Another thing is, I have been following this guy. Uh, yeah, I've been following this guy. You should be following this guy. I feel like it. Most amazing, most completed programmer. So I feel this guy is actually a computer scientist. I feel like it, and he has a playlist. Machine learning in C, and you should absolutely see this video. You should absolutely see this video. I watch the entire video and entire series. Not the entire series. So there are more. I actually watched till there's a lot more. I actually watched till 5 or 6, I think. Okay, so ML series in C by this I feel is an absolute watch to understand what really is a good base of mathematics and everything, right? To understand that, okay, how behind the scene maths work, right? And how behind the scene the entire look at that. He actually even generated videos from his C code. So he's that kind of a guy. Of course, it's not as good as GPT, but then he could do that, right? And this is where I started thinking that, okay, I should start, and maybe my love for maths comes back again, right? So this is one of the things that I have. It's not a full roadmap. It's still only like this is only for maths for machine learning. So this is not a full roadmap. After maths for machine learning, we have to go into a lot more deeper things. But I took help of ChatGPT and Claude and internet resources from Coursera and all that to figure out what are the things that we need for, having a good base of maths, at least a good base of maths for starting with machine learning and going to the next stage of building a small model using regression or things like that. So that's one. So if you look here, this is what we're going to do today. Linear algebra, which says how machines see data. Okay. That's what we're going to do today, and we're going to try and work some of the things today where we understand what vectors are, how to represent vectors, what are matrices, how to how to represent matrices, how to do a transpose, how to do a trace. I don't know what trace is, but then I also have to do matrix multiplication, things like that basically. And we're not going to use NumPy. I have used NumPy before. I'm not going to use NumPy. I'm not going to use pandas. I'm simply going to do it from scratch by myself. So that's what the plan is. So let's see. I have ChatGPT open, and I have a hell lot of things for its roadmap and things like that. And I have got a couple of websites open. Maths is fun. There's also an intuitive guide to linear algebra that I found via Kaggle. Okay. Then there's also a PDF, which again I found on Kaggle. I think this from Stanford. Yeah, this from Stanford, which is basically again one thing that I feel that I will be referring. And yeah, this is just that is fair. But yeah, I think we should get started. And I was first thinking of using Notepad, notebooks, but then I thought, okay, never mind, I'm just gonna write Python 5. Mm, okay. I can easily put in readmes and comments there, right? So that should be fair. Hmm. So where do we start? Let's look at what it says. Okay. Sorry. Hmm. Okay. Despite two linear algebra classes, my knowledge consists of matrices, determinants, and eigen something something, which I even don't remember. Determinants, I think, are like diagonals or something, but yeah, don't quote me. Why, let's try this. Name the course, but focus on single thing called matrices and vectors. Teach concepts like row column order with mnemonics instead of explaining the reasoning. Favor abstract examples, 2D vectors, 3D vectors, and avoid real world topic until the final. The survivors are physicists, graphic programmers, and other messages. We miss the key insight. Linear algebra gives you mini spreadsheets for your math equations. We can take a table of data, a matrix, and create updated data from the original. It's the power of a spreadsheet written as an equation. Here, the linear algebra introduction I wish I had with a real world stock market example. What's in a name? Algebra roughly means relationship. Grade school, blah blah blah. Without knowing x and y, we can still work that out. X plus y whole square is this thing. Okay, this is latex. I think latex render. That's why I cannot copy. Anyways, linear algebra means roughly line-like relationships. Same effect for every step. So I am really sorry. I have to do this. I'm really sorry for flashbanging, but otherwise you cannot see the image, right? I mean, maybe like this. Okay, maybe like this. Yeah, maybe like this. You have to see. Okay, this is still fucked up. So, okay, linear function, same effect for every step. Non-linear function effect varies. Okay, so as and when, so if I take this as a coordinate system, as and when x goes through, it has a very linear and a predictable way of going through. Is predictable the right word here? I don't know. Non-linear, it affects like in parabola or something, right? Okay. I'm sorry, I'm gonna flashbang you, but I'm really sorry for that. Straight lines are predictable. Imagine a rooftop. Move forward 3 horizontal feet relative to the ground, and you might rise 1 foot in elevation. Slope. Move forward 6 feet, you'll expect a 2-foot rise. Contrast this with climbing a toe. Each horizontal foot. I get you now. So every step that you take forward, you would have a predictable raise. Not predictable raise, you would have a linear raise. But there it would vary. Lines are nice and predictable. 3 feet forward has 1 foot raise, and going 10x far would be a 10x. Correct. 6 foot has 2 feet, then 3 plus 6 should have 1 plus 2. With 3 feet. Okay, makes sense. In maths term, an operation f is linear. The scaling input scales the output and adding input adds the output. Hmm. This right here, f of x equals a is a scalar number, is exactly this, right? You go 3 feet forward and you have a 1 foot rise, and then when you go 10x as far, so if you go 30 feet forward, it should give you a 10x raise. And the second one is in here, where if you add inputs, the outputs also gets added similarly. Hmm. An operation is a calculation based on some blah blah blah. Exponents are unpredictable. Okay. I think what it's trying to tell me is whenever you have a linear power of unknowns, that is when your function is more linear, but this is more quadratic function. So linear algebra is all about linear functions, right? So I'm, by the way, currently using hmm. What is hyperplane? A hyperplane is a flat subspace that divides an n-dimensional space into two half spaces. Okay. So what type of functions are actually linear? Plain old scaling by a constant. A function that looks like fx equals ax. In our roof example, a was 1 by 3. But life isn't too boring. We can still combine multiple linear functions. A of x is this into a larger one. Okay. So in algebra terms, we still talk about that mx plus c is mx plus c is a linear equation, but when we come to linear algebra, it is not. Something called affine or affine pronunciation.
Affine.
Affine. Okay. It's called affine. And here y equals mx. So it's basically shifted from origin. So for linear algebra, all lines are supposed to pass by origin. Is that what you're telling me? Exactly. Every line transformation or linear equation must pass with origin because linearity is required t0 equals 0. If it doesn't, it's not linear, it's a fine. So I feel this is something that we should that's something like that. फिर से मधुमक्खी खाने की कोशिश कर रहा है क्या? फिर से हाथ में लगेगा उसको. ML maths is what we call it. So Python. I have to look at Ubu. Nobody is aware. Python W. I think I should explore this once. I previously tried. What was the name? Python package managers. List. Pippin. I tried Pippin when I don't know. I faced a couple of issues with Pippin when I just said fuck you. I went back to Pip. So yeah. So till date I've been using Pip. So I think it's when activate. Yeah. Also, I have to take my Python 13.3. The newer version is 13.3.14. Anyways, what am I supposed to do? Okay. Why did you create all these things? Okay. Oh, I can directly spin up a. So in here, I'm gonna simply say that in linear algebra, a line must always pass by the origin. Line must, or let me zoom in this thing a little bit for you folks. Nation or linear equation must always. Can you just shut up? How do you remove this? multiply inputs by a constant. Okay, so we can still have functions where a equals ax, b equals bx, c equals cx, and then if you have everything together, it's basically additive. And then you can also scale. So one of the things you can do is scale. So um, one of the things you can do is scale, which also means I don't quite know how to do latex. And here, can I do latex, by the way? For some reason I cannot even render this thing properly, but I know who can. This most likely can build with agent. Shut the fuck up. Not that. Thank you. So can you do latex, by the way? I don't know how to write a latex thing. I think you write a func. Yeah. Let me not waste time with that. Maybe this is it. When I saved it here, why did you not reload? Do you see that? No, that is not something. I'm not very sure of exactly what's happened. So G is still linear since doubling the input continues to double the output. Okay, we have mini arithmetic. Multiply inputs by a constant and add the results. It's actually useful because when we split inputs apart, analyze them individually, and combine the results. If we allowed nonlinear operations like x squared, we couldn't split our work and combine the results because a plus b whole squared is not equal to a plus b squared. We know that, but there's an extra 2a. Okay. First, we should track a bunch of inputs. How about a list xyz? Not bad. We could write it xyz too, and onto that. Next, how we track our operations. Remember, we only have mini arithmetic, multiplications by a constant with a finalization. If our operation f behaves like x by z 3x 4 4y 5, we could abbreviate the entire function as 3 4 5. Okay, so we can think of vectors in that way. That the first one should be multiplied by 3, the second one should be multiplied by this, and according. So for any vector representation, I think let's see if that is correct. Is this correct? If this is a vector, it means with 3 unknowns x, y, z, the function we can derive is scale x, y, z 3 4 5 and add. So 3 4 5 should be equal to 3x plus 4y is 5z. So 3 4 5 simply represents the plane with the which satisfies this equation. 3x plus 4 plus 5z. Is that what you're doing in here? Okay. Okay. Get it. Only need the first input. So when you only need the first input, that is when you zero initialize the other things. So let's spice it up. How could we handle multiple sets of it? Let's say you want to run a function f on both a, b, c and x, y, z. Try this. but it won't work. F expects 3 inputs, not 6. We should separate the inputs into 2 groups. Much neater. Now we could run the same input through several operations. I'm confused now. Okay. Neat. Now you have getting organized. Inputs in vertical, operations in horizontal rows. Visualizing the matrix. Words aren't enough. Here's how I visualize input operations in the sync. Right. Hmm. So you have data and you have stack of operations. Actually, no, it's the other way now. You have an operation to perform. You have two data. Imagine pouring each input through each operation. So you put the data in here and it goes through the entire number of operations and you put it in here. Okay. As an input passes an operation, it creates an output item. In our example, the input ABC goes through the operation and outputs 3a plus b. It goes against the next operation G and outputs 3a plus 0 plus 0. Time for arithmetic. Matrix is a shorthand for our diagrams. Inputs A is equal to input 1 this thing. Operations M equals operation. Okay. Instead of using so this is the data actually, right? And these are the operations that you have to go through. So A has to go through 3a plus this thing plus this. Okay. You do it in this way. And then the numbering. Okay. But we are in a different world now, which I do not want to go. So this is another one of the things that I found again from Kaggle. Another resource. A vector is an ordered finite set of numbers. Vectors are usually written as vertical arrays surrounded by square curve. Okay. They can also be written as numbers separated by commas like this. So either it's a column based or it's a row based vector. Okay, but what is the difference between that? Like, that is a good question, I think, if that is even a thing. The elements or entries, coefficient components of a vector, are the values in the size, also called the dimension of the length of a vector, is the number of elements it contains. The vector above, for example, has size 4. Okay, its third entry is 3.6, which is a coefficient here. Again, I feel that it kind of becomes easier to manipulate and like think in terms of, oh, if I'm going to represent an equation in this term xyz, then these are the coefficients of this. So that kind of makes sense. I kind of remember the terms from school where you say a coefficient is basically the scale to which you are grading that x or y or z, something like that, right? Coefficient of a function, numerical factor that multiplies a variable in an expression. Okay, so 3x. Okay, cool. We often use symbols to denote. Okay, so we skipped over a little bit. The vector for above, for example, has size 4. This is a vector of size n is called an n vector. Okay, a 1 vector is considered to be same as a number. That is, we don't distinguish between a 1 vector 1.3 and the number 1.3. Okay, wait, but okay. Okay, so you just consider the lowest integral value. That is what the size, like 1 vector, 2 vector, right? But 1 vector is considered to be the same as a number. So if this was 2.6, is it going to be 2 vector? No, right? I don't understand that. A vector of size we often use symbols to denote vectors. We denote vectors and n vector using the symbol a, and the ith element is a of I. The subscript is, it's not something as interesting. Two vectors a and b are equal if we denote, okay, they have the same size and each of the corresponding entries is the same. A and b are n vectors, then a equals b, it means, okay, so these are all boring stuff. Give me something good. The numbers or the coefficients are scalars. So scalars is something which in physics or in maths basically doesn't, it means it has magnitude, and vectors means it has direction. So if I understand this correctly, if I say this is like, let's say this is, let's say 2 and 3, seems like a plausible reference. What are you sure you accept cancel? Shut up. Okay, so here I think I can close this side. So in here, this particular line, if I say, is having a magnitude or a distance of 3 square plus 4, so root 13, right? That is what I think is the scale. But if I talk in terms of a vector, it means it needs to have a direction on which side it's going. That is what vector is, and usually you write like this. And that is how we used to do in physics. And one of the things is that difference I remember is speed and velocity. Speed is just the magnitude of how fast you're going, but velocity comes with a direction, in which direction you're going. You're going up, you're going down, you're going left, right, things like that. Okay. The number of, okay, what did it say? Yep, here's what it means. A vector of n size, okay. So 3 is this. One vector is considered the same as a number. If a vector has just one element, there's no difference between it and a scalar value. Okay. Behave identically in LA operations, in linear algebraic operations, scaling, dot product, etc. Okay, so if you're multiplying with something, it's basically just a scalar value. That's all. Just a scalar value. There is no direction and only magnitude. Vectors add the concept of direction, but with just one component, there's no direction, only size. So in your maths, if I write 1, 2, 3, where is the direction? What? Tell me, what does it mean? Itself is ambiguous. It can mean two things depending on the concept. A point in the space is a location, position, or direction. It's a floating point in 3D. Yes. As a vector, it's the arrow from origin. Okay, so from perspective of linear algebra, we always talk in terms of origin. It has to be something from origin. Why LA doesn't care which one you pick? Linear algebra only deals with difference between points. So the point 1 to 3 and the vector from origin 1 to 3 are treated as the same mathematically. They have identical coordinates. Direction is orientation of that arrow in space. Magnitude is length of... this is exactly what I was talking about. So in here, this is the magnitude which is scalar, but if we talk in terms of vector, then it basically has to point from like origin to that. This is 2D space. They are giving an example. ChatGPT just gave an example of 3D space because I gave it a 3 vector. 1 to 3 has only direction when imagine it as an arrow. Okay, cool. Number of values of elements is blah blah blah. We'll focus on that cases in most applications where scalars are real numbers. In this case, we refer to vectors as real vectors. Occasionally, other types of scalars arise for example, complex numbers, in which we refer to the vector as complex vector. The set of all real numbers is written as R. This is boring stuff. It is sometimes useful to define vectors by concatenating or stacking 2 or more vectors, as in, so you're telling me this is stacked up 3 1 vector, A, B, C, and D. Wait. All are vectors. If B is an M vector, C is an N vector, and D is a P vector, that defines M plus M N P vector. A is equal to B1 till Bm. Okay, so I can have 2 or 3 vectors of multiple sizes, and this is more of a shorthand to say this is that, but this is more of a matrix that you're coming to, right? If I'm not wrong. Are vectors just 1D matrices? Set up correct? Vector can be viewed as specifically from one column or single. However, this is a useful interpretation, especially in computing, and doesn't capture the full theoretical definition of a vector, which is a member of vector space and geometry. Okay. Anyways, like for maths and programming, it makes sense, so it makes sense. The stack vector A can also be written as, okay, so this is just like giant pain in the ass where you can write it like this or write it like this. Just choose one thing and be done with it. Or maybe if you, sub vectors. I'm not kind of interested in all this maths right now and all this crap English right now. I want to know, the first warning concerns a range. In many computer languages, arrays are 0 to this thing, but in standard mathematical notation, n vectors are indexed from 1 to n. I don't care. A 0 vector is a vector with all elements equal to 0. Sometimes a 0 vector of size n is written up of n, where a subscript denotes the size. Unit vector is all or 1? No. Is a vector with all elements equal to 0 except one element. Okay, so unit vector is just one element. The ith unit vector is the unit vector with an I. Okay. So for unit vector, you have certain things. So if you can say E of 1, then it just means the first index. Again, like E of 1 and E of 2 is basically like offset of this thing. So E of ij is equal to 1 if j is equals this. So this is unit matrix, I think, right? Or I think it's called identity matrix. Is that correct? Can you just give me right? So yeah, holy shit, I remember the shit things. I remember it. Yeah, I'm just happy because again, like I loved math, but that love just faded off because of the society, because no one told me that math is so damn fucking important. And Yeah, anyways, uh, I love math, and I left all this concept behind saying it's not going to be useful anymore. So let's move on with life and learn Java code. Uh, but this is what is the basics of. It's not just machine learning or physics. Everything is based on these things, right? So it's quite fascinating that I'm still like slowly getting it back. That's fine. Okay. Anyways, one's vector. We use the rotation 1 and for the n vector with its elements equal to 1. We also write 1 as the size of the vector can be determined from the context. What do you mean by that? The 2 vector x. Okay. So because you're in a 2-dimensional space, so it's a 2 vector. Specifies a position. The 2 vector x represents a displacement in the plane by x1 and the first x. Okay. But what is the difference? Like how you're calling this as a vector and this as a vector? Both. Left, the 2 vector x specifies the position shown as dot, coordinates x1 and x2 in the plane. Right, the 2 vector, okay. Sparsity is sparse of many of its elements. I'm guessing it's like more sparse matrix thing that you have. Blah blah blah, all of that. 6 colors under RGB vectors. Okay. What is this? HSL? Interpreter, is that so? Can you just can I change in here? Oh no, this is hue, saturation and luminosity, I think. So this is not what we're looking at. So what the heck are we looking at? Because this definitely cannot RGB, or is it? No, it cannot be RGB. Also, this is cyan, magenta and yellow, so it has to be the combination. It has to be the combination of two things. Wait. One thing I quickly want to see here is that, so there's a color picker right here, and my hex is, this is 0, this is 255, this is 255, and it gives cyan, which means it's kind of the other way around. So you're saying that blue is off, the other two are on. Is that what you're saying? 6 colors under RGB vectors. It feels like that, right? It feels like that. What if I do the same thing in here? So where is my... Oh, I have to... Okay, I can actually do it here. Why am I going somewhere else? So this is now 255. 0 means off, and then this is 255 again, and I have magenta, which is correct. 3B82 F6. What if I pick this color and I say this? 242, 13, 242. I mean, it's very nearby. It's very nearby. 255, 242. You're offsetting this by 13. You're taking in 13 here. I don't know why, but for some reason it's done in that way. But that's quite fascinating. Okay, so you're representing colors in this way, but what is this representation? Okay, let's read this. An n vector can be used to represent n quantities or values in an application. In some cases, the values are similar in nature. For example, they're given the same physical units. In others, the quantity represented by the entries of the vectors are quite different from each other. We briefly describe below typical examples. I want to read this. The 3 vector can represent a color with its entries given red, blue, and green. Intensity values often between 0 and 1. So why is 1 off if the intensity is between 0 and 1? The vector 0, 0, 0 represents black because all of them are off. The vector 0, 1, 0 represents the... Wait a second, what? Wait. What is this? The vector and represents a shade of pink, which is 1... That is quite other way that you're doing, right? Of in the image what you're showing here. This would make sense because RGB, so G is 255 now. That is quite... I'm honestly not getting this. I do want to do this thing where I want to take the screenshot. Very honest. This is 1.2, right? Yeah, this is 1.2. Where is this guy? How are the colors matching against the words 0 to 1? 0, 1, 0 is green, but the image shows a different word. What is up with that? Missing something? I feel I'm missing something because this Stanford published book. But then, yeah, let's read this again. A 3 vector can represent a color with its entries given red, blue, green, intensity values between 0 and 1, and the vector 0, 0, 0 represents black. If 0 is off, it would make sense. This is black. But then in the other way around, in here, this is turned on, which means it should be red, but it shows something else completely. No, so it is still not like Endianness, something like that. It's not that, because it would still just be blue and not and not be this. But the question here is that, yeah, what does ChatGPT have to say? Excellent catch. You're not missing. It looks like the labels are mismatched. Yeah, I felt okay. Okay. Yeah, so whatever you're saying here doesn't quite match with this. But basically, any RGB you can represent in terms of intensity, and you can just say, like from 0 to 1, you can give it intensity, and you can just convert it to a hex, 0 to 255, something like that, and get a color out. So you can represent each color. You can represent each color as a 3 vector, but we are missing alpha. We are missing the alpha channel. So if you only take 3 channels into consideration, I think you can do that. Okay. So time series. Okay. I think we should read this part because it has some interesting things probably I can learn from. An n vector can represent a time series or a signal, that is, the value of some quantity at different times. The entries in a vector that represents a time series are sometimes called samples, okay, especially when the quantity is something measured. An audio signal can be represented as a vector whose entries, but how is an audio signal a vector? But again, I think vector and physics vector with a magnitude is different. Here, vector simply means a 1D array, because just with time you can represent the magnitudes, and you can, like, if you have so if your sampling rate is I'm not good with maths in this case, but if you're sampling where you are taking like, let's say 60 samples per second, within 60 like every second you have a marker, you would have dots on that, and you can just generate the graph from there. I forgot what it's called. Heat sound graph called spectrogram. Okay, so this is also not something I think there's a different word for it. Graph showing sound samples, or oscillogram. No. I think it is spectrogram. Or something. Yeah. Anyways, something like histogram, but it's not histogram. Yeah. So a vector might be hourly rainfall at some location over some period. When a vector represents a time series, it's natural. Okay. So you have a vector which is 8 by 8 image, so it's 8 pixels per 8 pixels. A monochrome image is an array of m cross m pixels, square package with uniform grayscale level, with m rows and n columns. Okay. Each of the mn pixels is a gray or an intensity value with corresponding 0 and 1. Other ranges are also used. An image can be represented by a vector of length mn with the elements giving grayscale levels at pixel. This is a very low resolution typical in her, but with the vector arranged proof-wise, the associated 64 vector, because it's 8 cross 8, is like this. So you have to explicitly know that it's an 8 cross 8. That is where you can divide it at that point. Otherwise, it would be represented by a matrix, right? Otherwise, you need to have some information sent over. If you're sending this image across the network, I feel like, okay. It is common practice to variation, blah, blah, blah. Word count vectors are used in computer. Okay, this is what is interesting. Word count vectors are used in computer-based document analysis. Each entry of the word count is the number of times associated dictionary appears in the document. Okay. Each entry of the word count vector is a number of times an associated dictionary word appears in the document. So there is also one more algorithm I know, TF-IDF, which is term frequency inverse document frequency, which was used by Google for ranking, I believe. So yeah, it's something like that, where you have certain number of words which appears in the document, and you're given the number of these things here. A snippet of text. Just basically did that. Okay, this is what I was looking for, minor front. So this is what I'm looking for. Vector addition. Two vectors of the same size can be added together by adding the corresponding elements to form another vector of the same size, or the sum of the vectors. Vector addition is denoted by the sum plus. Thus, the symbol plus is overloaded to mean scalar addition. Thus, the symbol plus is overloaded to mean scalar addition when scalars appear on its left hand and right side. And vector subtraction is of the same example. Also, can I copy this guy? No. How do I even represent that? Okay, so you're simply doing this thing here. So if you are looking at vectors plus vector, well, you don't have to do that in here. Niche. So kind of don't need that, I think. Self values is a list of floats, and this can come from here, and I think there is a Thunder method called add. Yes, there's a Thunder method called add. So this can be beat, which is again a list of floats, and to return back a list of floats. I mean, we can, I think it's called void. No, void. I forgot. I think you don't have to do it. Doesn't return anything. So one of the things I want to do here is that I want to make sure that rows and columns are same. So rows, columns, self rows columns equals self values of 0. Well, I am already kind of taking it into account that it's always Let's see, right? How do you do this? How do you do columns? Okay, I've been streaming for almost 1 hour now. I want to quickly take a break for 5 minutes, and then I'm gonna be back, and then we're gonna continue on this one. Okay, I'm gonna quickly take a break, and then we're gonna continue. So yeah. Okay, we are back, and we were talking about this, right? So this is giving an this thing because expected size got float instead. Uh-huh. I know. Okay. Because this is not a list of lists, it's a vector. So columns, self dot columns. Columns equals length of self values and self columns and v2. So let's call this v1 is v2 dot values. Also, this is gonna be a vector, and I don't want to return a vector. Can you just shut up? Thank you. I want to do this. And what you're trying to say, unresolved attribute v as vector. My bad. This is what I was looking for. Okay. If v1 columns is not this, yeah, alright, vectors must be of the same length to act, yeah. Otherwise, what we're gonna do here is that okay, so for I in range of v1 columns, self values, yeah, this is what we have to do. This is what we have to do. And return self. Why do we have to return self in here? We don't want to return self. We can return self. I know for one thing within this it cannot do that, so I have to do string. I don't quite know why, but maybe it's a good time to. Okay, we'll study about that later on. So this is what this is, and then for sub, take this, and here is this thing except do that. Okay. One thing you can do is check size check. Okay. So you have self and you have vector this thing. So here you can collapse this into self dot size check and pass in v2. This here can also be collapsed. Self size. Okay. And here you have to pass v, and you can put this in here, which means you can nuke everything. And length of self values. This is what you can. This is what you can do. Right. This is what you can do. And let's do a test. So here, if name is name, you can see vector 1 is this. Yeah, let's see. So you say vector 1 is this thing, and this. So in here, what you can say is Python. Wait. Oh, because of that. Okay. After subtraction, what happened in here? Shadows came from outer scope. What outer scope we talking about? Okay. Hmm. Because I know why. Because we are changing the values, we are not returning a new one. We are changing the values. So I feel we don't want to do that. Do we want to do that, or do we want to change the vector? We want to change the vector. So vector v is this thing. Okay, well, you don't write like that. Sorry. So v is this thing, and then what you can do in here is we append. Is it not append? And you want to return v. And here, save that. Now it works. Okay, what are the operations can you do? Vector addition is commutative. A plus b is equal to this is associative. Okay. This is an example where the size of the vector follows from the context. It must be the same size as a minus a is 0. Subtracting a vector from itself means the 0 vector. Here to the size of 0 is the same. To show that this property is hold, I know this thing. So here, what happens is that if you're trying to say that vector a plus vector b, it is basically okay. So how it? I think I have actually opened, yeah. If I'm not wrong, this is how vectors work. So this is a new vector. This is a vector a, and then there is another vector which is b. If you want to add a plus b, what you have to essentially do is move a in here. So b dash, you move that, and then you say that the origin of a, my bad, origin of a, the origin of to the head of b is a plus b. This is what it is, right? Now let's say we have the same diagram. We have the same diagram. We have the same thing in here. I'm going to remove this. I'm going to remove this. Okay, I'm going to remove this. This. So here it is. So what we try to do is we move a like this, and we call it a prime. And essentially this is going to be a plus b. So as you can see here, it is the exact same thing. It is the exact same thing if I overlap these two things. This is what two vector additions are. So you take one of the vectors and you move its origin to the end of the other vector, and then you create a vector from the origin of the first one to the head of the other. So whether you shift this one B to the top of A, or you shift A to the top of B, it lands up with the same vector. Vector addition is called associative. Sorry, commutative. A plus B is equal to plus C. Vector addition is associative. A plus C should be equal to A plus B plus C. Yeah. This is nothing but A plus B plus C. So let's try to do this exactly how we did here, right? So we have this. Let's do it with the original colors that we had. Then you have this. Then you have one of them, A. You have B, and then you can have another, which is C. Okay. So for A plus B plus C, what you have to do is you first, let's say, move this to here. So this kind of becomes an A plus B. Okay. Then you move this guy in here. So your final answer would be this. What if we do the other way? What if we do the other way? So let's delete this, 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 and this. So now we want to move B in here. So this right here is B plus C. And then we move this guy in here. And this is what your final answer is. A plus B plus C. Is it? Yeah. It is the same. It is the same. It's kind of difficult to map, but yeah, it's the same thing. So we can say, yeah, from diagrams we can see that this is what it is. That kind of gives me an idea of a good video. Using a video to the space vectors, we can show how vector addition is commutative and associative. And this is going to be here. Anyways, yeah, that makes sense. Some programming languages for manipulating vectors define the sum of a vector as scalar as a vector obtained by adding the scalar to each element. This is not the standard mathematical notation. However, we will not use it. Even more confusing, in some computer languages, the plus is used to denote concatenation of this thing, which means putting one array after another. While this notation might give a valid expression, it is not standard mathematical notation and we will not use it in this book. In general, it is very important to distinguish between mathematical notation for vectors, which we use, and the syntax for specific computer languages or software packages. It's okay. This is quite interesting. Scalar vector multiplication. So scalar vector multiplication, another operation is scalar multiplication or scalar vector multiplication, in which a vector is multiplied by a scalar, which is done by multiplying every element of the vector by the scalar. Scalar multiplication is denoted by juxtaposition, typically with the scalar on this left as in, okay. So scalar multiplication can also be written as this thing, and it means the same. By definition, alpha a equals a alpha for any scalar alpha and any vector a. This is called commutative property of scalar vector multiplication. It means that the scalar vector multiplication can be written in either order. A linear combination, okay, linear combination of unit vectors and things like that. Special linear combinations. Sorry. So I think what we can another do here is that def scale self factor, which is a float, and it turns this thing. So in here, p equals vector, and then for values in self dot values, we can simply say parent value this thing, and in here return p. Okay, so now yeah, inner product, also called dot product of two n vectors, defined as a inner product of b is a1 into b1 plus a2 into okay. If you have something called mul, so let's first do dot. Nothing called dot, so let's just do dot. So what v2 from outer scope, which we acha this okay. So dot product, or we can simply say inner product, there's an outer product, there's none, right? So it directly goes to inner product. Okay, the affine combination for, okay, I'm not going to go into that. Standard inner product, or also called the dot product of two n vectors, is defined as like this: the sum of the product, the sum. Okay. So if you say dot product, what you would do here is first you would do a size check on other. You do that. Is my GitHub completions? It was not, so that's why it was shitting so much. Okay, so after that, what you can do here is that for I in range of uh, length of self values. So here you can do that, and you can say this here is self values of I into self. We have to add them together. But yeah, we can do that. Self dot sorry, other dot values I, and you can do a sum of its values is this, and you can simply return that. So v1 dot v4 dot product is this thing. So print dot product is this, and what are we expecting in here? So v1 is this thing, and we did v4 is this, right? So this here would be -3, this would be -6, and this would be -9. So total, what do you get? 15, 18. So let's see if that is right. -18, that is correct. Okay. So the dot product is basically nothing but multiplication of each and individual scalars, and then you add them up together. That's your inner product or your dot product. Okay. And dot product is also commutative, right? Because A into B, A dot B and B dot A would be the same thing, but not the other way around. Just checking if I got any chat in here. No. Okay, cool. Block vectors. If the vectors A and B are block vectors and the corresponding blocks are the same sizes, then we can say this thing. Okay. The inner product is useful in many applications, a few of which we list here. Co-occurrence. If A and B are n vectors that describe occurrences, that is, each of their elements is either 0 or 1, then A inner product of B gives a total number of indices for which A and B are both 1. That is the total number of co-occurrences. If we interpret the vectors A and B as describing subsets of in objects, then this thing gives a number of objects in the intersection of two subsets. Okay. So the question is, where do you give an answer, right? You have to give an answer somewhere. Okay. Now, from mathematical point of view, I think this is not correct, where you have 1 to 1 and the other way around. Because the brackets are called I forgot the name, but it's block vectors, so it's vector of vectors. So we have to think of in terms of, oh, this is one vector, and this is 3 vector, so it's not the same. In here you have one vector, and in here you have a single block of 3 vector, right? Is that right? Is that right, meine Freunde? I may be completely off. Where on earth did you give any answers? Don't give any answers. Holy shit, you cannot. Exercises. I want to know if you actually give answers to those exercises or you're just giving exercises. No, don't. Okay. So I think we did some good research on vectors, where what is a vector, how do you addition, how do you subtract, how do you do a scalar factoring, and how do you do a dot product, or which is also called an inner product. Okay. Yeah. The only thing here is that we did underscore dunder add, not underscore. We did dunder add so that we can simply do v1 plus v2. So it's going to override it. One thing I quickly want to see here is that what if I say this is also multiplication. Can we simply do into this thing? I feel like we can. And we can call this v6. v6. I probably should have overridden this thing, but okay. Wait, that's weird. Oh no, it's here. Yeah, so that's something we can do. Okay, so what we can do is we can simply call self scale factor and we return this. That's all. We can do that. Or the other way around. I mean, yeah. So, what all things we learned today? First thing is what a vector is. Vectors are nothing but a series of coefficients on top of which you can do certain things as an addition, subtraction, multiplication, scaling. Multiplication can be of a scalar. Multiplication can also be with a different vector, which is called a dot product. And yeah, that is basically it. That's basically it. That is what I would say we kind of learned today. This is what we were able to learn. And, very simple, small. But yeah, what are the operations we can do with? I don't see anything else in here. So these are more mathematical stuff, which I don't want to waste time right now. I don't know how important it is. Definitely not important at this particular stage, I would say. Perfect start. This is exactly the blah blah blah. You have now implemented vector representation, scalar, and alias dot scale dot product validation for dimensionality. That stage covers stage 2, 3, 4. Oh, by the way, I don't know if I actually gave this thing. So this is something that I did. So yeah, where scalars and vectors. So this is the first thing that we are trying to work with. What is normalize? Vector normalization. Vector normalization is a process of scaling a vector to length of 1 while keeping its direction the same. To normalize a vector, you divide each component by the square root of the sum of the square. For a vector x and y, the magnitude is x squared plus y squared. Okay, so this is what the magnitude is. And you divide each component by that, and this scales the vector down to a length of 1. That makes sense. Normalized vector is this. Okay. Okay. So I think I'm gonna end the stream tonight. I think I at least got the initial um, guess of what's gonna happen, uh, what's gonna happen, and things like that. In the next stream, we're gonna do the same things. We're gonna first, I mean, magnitude, normalize, things like that are pretty simple to understand. But I also want to understand that why exactly, right? What exactly is happening? Things like that. I do want to understand that first, and an angle between vectors and all of those things, like projection. What exactly is projection? String repertoires, like just for printing stuff and all that, and then we can move on to span, basis, orthogonality. Yeah. So next thing I would be doing here is that yeah. So in the next stream, I would be basically trying to go over all the other things of linear algebra, and I would also recommend linear algebra free camp. Yeah, so there's linear algebra full, there's a linear algebra here. I mean, there are 3 videos already, out of which there are 24 hours of videos right there. So I think it's kind of cool. And it's also in here. Oh, just talks about this thing. But I mean, this is also something which folks should refer to for this kind of things. Yeah. So I'm gonna put all of these references somewhere so that it's easier for me also. So that didn't work out quite well, but I can quickly point out here. So this is something that we haven't done. This is also something I don't think is really quite useful, but this is, and yeah, I don't feel anything else is right now very useful. So thank you so much, whoever joined in. Thank you. I'm gonna end the stream today, and I'm gonna call it a day. And I'm still not pushing this stuff to GitHub because I don't think so it's really that juicy right now. But yeah, tomorrow again I would be coming online and I would be continuing with this. This is something that I would want to continue in more rapid paces than the other series that I kind of do. Again, it kind of depends on tomorrow's mood, where I come and say, because I might study this thing in the morning when I might not stream. In the evening when I'm streaming, I might just do basic, right? So kind of completely depends on like what I did in the morning, what I studied in the morning, and then that. But yeah, let's see. Till then, thank you so much for joining. You have a great Saturday night, and thank you.